Good day, engineers. I am your Tito engineer, and today we will discuss important board exam situational problems from May 2011 CE board exam in the hydraulics and geotechnical engineering subject. May 2011, Geotechnical Engineering. Problem number 1. Given the following properties of soil, specific gravity of solids, G equals 2.70. Void ratio, E equals 73%. Degree of saturation, S equals 92%. Number 1. Determine the nearest value of moisture content of soil. Number 2. Determine the nearest value of dry unit weight of soil. Number 3. Determine the nearest value of moisture content when the soil is saturated. This problem is included as all about soil properties. The problem only involves calculation of volumes basic soil properties, and it does not need to have an illustration. This problem is more on formula and principles based. For our solution to the first part of the problem, we will recall the relationship between soil properties, namely, specific gravity, moisture content, degree of saturation, and the void ratio. It can be recalled that the product of specific gravity of soil solids and the moisture content is equal to the product of degree of saturation and the void ratio. Or simply, GMC is equal to SE. Substituting values, we get 2.7 times the moisture content is equal to 0.92 times 0.73. Our moisture content therefore is equal to 24.87%. For our solution to the second part of the problem, we will recall the formula for dry unit weight of soil, that is, specific gravity over 1 plus void ratio multiplied by the unit weight of water. Substituting values, we get 2.7 over 1 plus 0.73 times 9.81 kilonewton per cubic meter. Our dry unit weight therefore is equal to 15.31 kilonewton per cubic meter. For our solution to the last part of the problem, we have to take note that the soil is already saturated. In this case, our degree of saturation is equal to 100% or just 1.0 in decimal. Recalling the relationship of basic soil properties given by GMC is equal to SE. Substituting values, we get 2.7 times moisture content is equal to 1.0 times 0.73. Solving for the moisture content, we will get moisture content is equal to 27.04%. Problem number 2. The result of a triaxial test on a cohesive soil is as follows. Angle of shearing resistance, phi equals 29 degrees. Cohesion, C equals 31 kilopascal. Maximum shearing stress, R equals 65 kilopascal. Number 1. Compute for the value of the cell pressure at failure in kilopascals. Number 2. Compute for the value of the maximum principal stress at failure in kilopascals. Number 3. Compute for the value of the normal stress at the plane of maximum failure in kilopascals. We begin by illustrating the problem. Taking note that in actual board exam, it is seldom that the examiner will provide illustration, so we have to do it on our own. Note that we have to be familiar on how to plot the stresses both for cohesive and non-cohesive soil, since it has higher chances of being in the actual board exams. For easy reference, I just labeled it with different variables for easy recognition. For our solution to the first part of the problem, from the illustration, tangent of angle phi is equal to the cohesion C over x. Substituting values, tangent of 29 degrees is equal to 31 kilopascal over x. X value therefore is equal to 55.925 kilopascal. Note that this is still not our final answer for part 1. Carrying on, from the same illustration, sine of angle phi is equal to the radius of more circles r over x plus sigma 3, or the cell pressure plus sigma n plus c. Take note that sigma n plus c is just equal to the radius of more circle. Simplifying it further, sine phi is equal to radius over x plus sigma 3 plus radius. Substituting values, we get sine 29 degrees is equal to 65 kilopascal over 55.925 kilopascal plus sigma 3 plus 65 kilopascal. Using the shift solve function of our calcu, we get sigma 3, or cell pressure, is equal to 13.148 kilopascal. For our solution to the second part of the problem, from the illustration, sigma 1, or THA maximum principal stress, is equal to sigma 3, or cell pressure, which can also be called minimum principal stress, plus twice the radius. Substituting values, 13.148 kilopascal plus 2 times 65 kilopascal. Sigma 1, or maximum principal stress, is therefore equal to 143.148 kilopascals. For our solution to the last part of the problem, from the illustration, sigma n plus c is equal to sigma 3 plus r. Substituting values, 13.148 kilopascal plus 65 kilopascal. Normal stress at the plane of maximum failure is therefore equal to 78.148 kilopascals. Problem number 3. Thick layer of saturated clay has a moisture content of 59%. The specific gravity of soil solids is 2.68. The water table is on the ground surface. Number 1. Determine the density of clay in grams per cc. Number 2. Determine the effective stress in kilopascal at a depth of 30 m. Number 3. Determine the total stress at a depth of 30 m. This problem is included is all about soil properties. The problem only involves calculation of volumes, basic soil properties, and it does not need to have an illustration. This problem is more on formula and principles based. For our solution to the first part of the problem, we will recall the relationship between soil properties, namely, specific gravity, moisture content, degree of saturation, and the void ratio. Take note that the water table is on the ground surface, therefore our soil is completely saturated, therefore our degree of saturation, or S, is equal to 1.0. GMC is equal to SE. Substituting values, we get 2.68 times 0.59 is equal to 1.0 times E. Our void ratio therefore is equal to 1.5812. We will recall the formula for density of soil in gram per cc, that is, specific gravity times 1 plus moisture content over 1 plus void ratio multiplied by the density of water in gram per cc. Substituting values, we get 2.68 times 1 plus 0.59 over 1 plus 1.5812 times 1 gram per cc unit weight of water. Our density therefore is equal to 1.651 gram per cubic centimeter. For our solution to the second part of the problem, we will recall the formula for unit weight of soil, that is, specific gravity times 1 plus moisture content over 1 plus void ratio multiplied by the unit weight of water. Substituting values, we get 2.68 times 1 plus 0.59 over 1 plus 1.5812 times 9.81 kilo Newton per cubic meter. Our unit weight therefore is equal to 16.195 kilonewton per cubic meter. Take note that we are after for the total stress at 30 m, so this is still not our final answer. Formula for stress in soil is equal to unit weight times height. Substituting values, 16.195 kilonewton per cubic meters times 30 meters. Total stress at 30 meters therefore is equal to 485.85 kilopascals. For our solution to the last part of the problem, we will recall the formula for effective stress, that is, effective stress is equal to total stress minus the pore water pressure. Substituting values, we get 485.85 kilopascals minus 9.81 kilonewton per cubic meters times 30 meters. Effective stress at 30 m is therefore equal to 191.85 kilopascals. Problem number 4. A confined aquifer is shown in the figure. This aquifer has a source of recharge located as shown. The hydraulic conductivity of the aquifer is 45 meters per day with porosity of 25%. The piezometric head surface in the two observation wells 1650 meters apart are at elevation 65 meters and 60 meters respectively from common datum. The aquifer has an average thickness of 25 meters and an average width of 4 kilometers. Number 1. Determine the rate of flow of water through the aquifer in cubic meters per day. Number 2. Determine the value of seepage velocity in m per day. Number 3. Determine value of the time travel from head of aquifer to a point 4.2 kilometers downstream in days. In this particular problem, it is clearly stated that we will be having a figure, so no need to illustrate the problem on your own. For our solution to the first part of the problem, we will recall the formula for discharge through soil. That is, discharge is equal to hydraulic conductivity K times hydraulic gradient I times the area A. From the problem, we can identify some given values, namely, hydraulic conductivity of 45 meters per day, porosity of 25%, heads H1 equal to 65 m and H2 equal to 60 m, the length equal to 650 meters, thickness of 25 meters, and width of 4 kilometers. From the formula Q is equal to KIA, where K is equal to 45 meters per day. Our hydraulic gradient can be calculated as the difference of head over the length, or 65 meters minus 60 meters over 1,650. Hydraulic gradient is therefore equal to 1 over 330. Area, on the other hand, has a formula of width times thickness, or 4,000 meters times 25 meters. Area therefore is equal to 100,000 square meters. Substituting all of these values to our formula, discharge is equal to 45 meters per day times 1 over 330 times 100,000 square meters. Discharge or rate of flow is therefore equal to 13,636.36 cubic meters per day. For our solution to the second part of the problem, We will recall the formula for seepage velocity, which is equal to velocity over the porosity, or can be equated as hydraulic conductivity times hydraulic gradient over porosity. From the formula, Vs is equal to Ki over N, where K is equal to 45 meters per day. Our hydraulic gradient as calculated before is equal to 1 over 330. Porosity, on the other hand, is 25% or 0.25 in decimal. Substituting all of these values to our formula, seepage velocity is equal to 45 meters per day times 1 over 330 over 0.25. Seepage velocity is therefore equal to 0.545 meters per day. For our solution to the last part of the problem, we will recall the formula time in our physics. From velocity is equal to distance over time, we can get time is equal to distance over velocity. The velocity that we will use here is the seepage velocity. From the formula, time is equal to distance over seepage velocity. Distance is equal to 4.2 kilometers or 4,200 meters. Seepage velocity from our previous question is equal to 0.545 meters per day. Substituting all of these values to our formula, time is equal to 4,200 meters over 0.545 meters / day. Time is therefore equal to 7,706. 42 days. Problem number 5. A tank 12 m high is to be filled with oil with unit weight of 9.4 kilonewton per cubic meters as shown in figure. Neglect the weight of tank number 1. Determine the compression index of the clay layer. Number 2. Determine the settlement under the center of the tank in M. In this particular problem, it is clearly stated that we will be having a figure, so no need to illustrate the problem on your own. For our solution to the first part of the problem, we will recall the formula for compression index. That is 0.009 times liquid limit minus 10. From the problem, we can identify some given values, namely, for sand unit weight of 18.88 kilonewton per cubic meters. Clay has the following properties. Clay unit weight of 17.31 kilonewton per cubic meters. Void ratio of 1.27. Liquidity index of 0.645. Plastic limit of 20%. Moisture content of 40%. We first need to solve for the liquid limit in order to use the formula of compression index. From the liquidity index formula, liquidity index is equal to moisture content minus plastic limit over liquid limit minus plastic limit. Substituting values, we get 0.645 is equal to 0.40 minus 0.20 over liquid limit minus 0.20. Using shift solve function of our calculator, liquid limit is therefore 51%. Substituting this value to the compression index formula, compression index is equal to 0.009 times 51 minus 10. Compression index therefore is equal to 0.369. For our solution to the second part of the problem, we will recall the formula for primary settlement. That is, settlement is equal to height of clay times compression index over 1 plus void ratio log of final stress over initial stress. Height of clay from the figure is 14 m or 14,000 millimeters. Compression index from our last question is equal to 0.369. Void ratio is equal to 1.27. For our initial stress, we need to determine the effective stress from the ground up to the middle part of clay only. Take note that our groundwater table is at the ground surface. Effective stress is equal to 18.88 kilonewton per cubic meter minus 9.81 kilonewton per cubic meter times 3 meters plus 17.31 kilonewton per cubic meter minus 9.81 kilonewton per cubic meter times 7 meters. PO is therefore equal to 79.71 kilopascal. For our final stress, it is just equal to initial stress plus our delta P, or increase in pressure induced by our tank. Or PF is equal to PO plus delta P. PF is equal to 79.71 kilopascal plus 9.4 kilonewton per cubic meter times 12 meters. PF therefore is equal to 192.51 kilopascal. We can now use the formula for settlement. Delta H is equal to 14,000 millimeters times 0.369 over 1 plus 1.27 log of 192. 51 kilopascal over 79.71 kilopascal. Our settlement therefore is equal to 871.48 millimeters. Problem number 6. A pre-stressed concrete pile, 360 millimeters by 360 millimeters in cross-section, is to be driven in a clayey soil of unit weight 18.5 kilonewton per cubic meters as shown in the figure. The pile has a design capacity of 360 kilonewton. Use factor of safety of 2. The unconfined compression shear strength, CHU, of the soil is 110 kilopascal. Use NC equals 9. Number 1. Determine the end-bearing capacity of the pile in kilonewton. Number 2. Compute the skin friction in kilonewton to develop along the shaft of the pile. Number 3. Compute the length of pile in meters if frictional constant alpha is equal to 0.75. In this particular problem, it is clearly stated that we will be having a figure, so no need to illustrate the problem on your own. This problem can also be solved without the use of the illustration. For our solution to the first part of the problem, we will recall the formula for end-bearing capacity. That is cohesion times cohesion factor times the area of the tip. From the problem, we can identify some given values, namely, cross-section, a square section of 360 mm by 360 mm, unit weight of 18.5 kilonewton per cubic meters. Design capacity of 360 kilonewton. Factor of safety of 2.0. Unconfined compression strength of 110 kilopascal and NC of 9.0. Take note that if NC is not given, we can use 9.0 as value for NC for clayey soils. QB is equal to C times NC times area of the tip. Cohesion C can be solved using the formula. Cohesion is equal to 1/2 of the unconfined compression strength, or 1/2 of 110 kilopascal equal to 55 kilopascal. NC is equal to 9.0. Area, on the other hand, is the area of the square section, or 0.36 meters times 0.36 meters, equal to 0.1296 square meters. Substituting values to our working equation, QB is equal to 55 kilopascals times 9.0 times 0.1296 square meters. End-bearing capacity therefore is equal to 64.152 kilonewton. For our solution to the second part of the problem, we will recall the formula for skin friction. That is, skin friction is equal to ultimate capacity minus the end-bearing capacity. There are also other formula for skin friction, but it does include length, which we still do not have. QF is equal to QU minus QB. From the first part, we got QB is equal to 64.152 kilonewton. For our QU, we can use the formula for factor of safety since we are given with that value. Factor of safety is equal to QU over QA. Substituting values, 2.0 is equal to QU over 360 kilonewton. Q therefore is equal to 720 kilonewton. Substituting this one to our working equation, we will get 720 kilonewton minus 64.152 kilonewton. Skin friction therefore is equal to 655.848 kilonewton. For our solution to the last part of the problem, we will recall the other formula for skin friction. That is, skin friction is equal to frictional constant times cohesion times perimeter times length. QF is equal to alpha CPL. From the second part, we got QF is equal to 655.848 kilonewton. Alpha is 0.75. Cohesion is 75 kilopascal. Perimeter is equal to 4 times the side of square, or 4 times 0.36 m equal to 1.44 meters. Substituting the values to our working equation, we will get 655.848 kilonewton is equal to 0.75 times 55 kilopascal times 1.44 meters times the length. Length therefore is equal to 11.04 meters.